Welcome to the Explainer. So if you're writing Scala, you're pretty much using the collections library all day, every day. But have you ever stopped to think about why it's designed the way it is? Today, we're going to pull back the curtain and really look at the genius engineering that makes Scala's collection so powerful, so safe, and honestly, so efficient. All right, here's our game plan. We're going to start with the absolute foundation, the core philosophy, immutability. Then, we'll dive into the real-world trade-offs you have to make with sequences and sets. After that, we'll unleash the power of FlatMap, see how the type system keeps us safe with variants, and wrap it all up with a killer optimization technique using views. Let's do this. Okay, first up, the single most important idea in the entire library, the bedrock of everything else we're going to talk about, immutability. And trust me, this isn't just some nice-to-have feature. It's a deep-seated design philosophy that changes everything. So let's see this in action. On the left, you've got the default immutable style. See that? When we add 4 to our list, the original list is still there, completely unchanged. What we get back is a brand new collection, list 2. Now, compare that to the mutable world on the right. That plus equals operation, it changes the buffer right there, in place. It's a side effect. And those things can cause all sorts of headaches down the line. This one difference is absolutely crucial. So why is this the default way of doing things in Scala? Because the payoff is massive. For starters, you get thread safety for free. You can share these collections across threads all day long without worrying about locks or race conditions. That's a huge win. Plus, your code just becomes so much easier to reason about. No more hidden changes, a function gets a list, it can't mess with it behind your back. And get this, it's even efficient. Thanks to something called structural sharing, that new list you create can actually reuse most of the memory from the old one. It's really clever. Okay, so now that we've got immutability down, let's look at where the rubber meets the road with our first major trade-off, sequences. You might think all ordered collections are basically the same, but in Scala, that's definitely not the case. Picking the right one is all about knowing how you're going to use it. Right, let's start with the classic, list. It's a linked list, and the train analogy is perfect here. Think of each element as a train car, linked only to the one after it. Because of this, anything you do at the very front, checking the engine or what we call the head, or hooking on a new car at the front, which is prepend, is super fast. But what if you need to get to the 500th car? Well, you've got no choice but to walk through all 499 cars in front of it. Not so fast. Now, on the other hand, we have vector, which is Scala's go-to default for indexed sequences. And it is a totally different animal. Forget the train. Picture a huge but very shallow, branching tree. It's kind of like a crazy efficient index. Because of this structure, the system can figure out the path to any element almost instantly. So getting to the 500th element or the 5 millionth element takes pretty much the same amount of time. It's incredibly fast for random access. And this chart just lays it all out clear as day. Look at list. For head and prepend, you see O of 1. That's constant time. It means it's blazingly fast whether the list has 10 items or 10 million. But look at apply, that's getting an item by its index, or append at the end. They're O of n, linear time. That's a performance killer. It means the operation gets slower the bigger the list gets. And then you look at vector. It's just a sea of effectively constant time. It's a rock star for all-around performance, and that's exactly why it's the default you should probably be using most of the time. Okay, we see a very similar story when we look at sets, the collections where every single element has to be unique. And the trade-off here is even simpler. It boils down to one question. What do you care about more, raw speed or a predictable order? So, your default is hash sets, and this thing is built for pure, unadulterated speed. It uses a super smart data structure that basically gives you O of 1, or constant time, performance for just about everything. Adding, removing, checking if something's in there, it's incredibly fast. The catch? The order of elements is totally unpredictable. If you iterate over it, who knows what you'll get? But if you absolutely need your items to stay sorted, then you use tree set. It pays a small performance price, but in exchange, it guarantees your elements are always in order, no matter what. So how does TreeSet pull off this magic trick of being both sorted and efficient? Well, the secret sauce is this really cool data structure called a red-black tree. You can think of it like a binary search tree that's obsessed with staying balanced. Whenever you add or remove an item, it does this little dance, rearranging its nodes to make sure no branch gets too long. It's this constant self-balancing that guarantees its performance won't fall off a cliff, keeping everything nice and fast. All right, we've got a good handle on the data structures. Now let's talk about the operation that really unlocks the functional superpowers of these collections. I'm talking about the one, the only, flat map. To really appreciate what flat map does, you first have to see the mess that a plain old map can get you into. Imagine you map over a list, and the function you're using also returns a list for each element. What you end up with isn't a simple list, it's a list of lists. It's nested. And most of the time, that's really not what you wanted. And this is where FlatMap comes in to save the day. The name tells you everything you need to know. It does a map, and then it flattens the result. It's like doing a map and then a flatten all in one go. So it takes that awkward nested list of lists and just collapses it down into one beautiful, simple, flat list. Problem solved. Okay, but here's where we go a little deeper. FlatMap isn't just a handy trick for lists. It's actually a fundamental concept in functional programming. It's the key operation that lets you chain together computations that live inside some kind of context or container. That container could be a list or an option that might be empty or a future that hasn't finished yet. FlatMap lets you keep working with a value inside that container without all the messy boilerplate of checking and unpacking it. It's the engine that powers clean, elegant functional code in Scala. All right, let's switch gears and talk about the safety net. How does Scala's powerful type system actually stop us from shooting ourselves in the foot when we use these collections? Well, that's where a concept called variance comes in. Variance can sound complicated, but the core idea is pretty simple. Let's take the main one for immutable collections, covariance. If a dog is a type of animal, then it makes sense that a list of dogs can be treated as a list of animals. It's safe because the list is immutable. You're only ever taking things out, and every dog you take out is definitely an animal. But now think about a mutable collection. If you could treat a mutable array buffer of dogs as a buffer of animals, a piece of code somewhere else could try to add a cat to your buffer of dogs, and that would be a complete disaster. So to prevent this, mutable collections are invariant. The compiler just says, nope, an array buffer of dogs and an array buffer of animal are totally unrelated types. It's a safety feature that stops you from making a huge mistake. And finally, let's talk about a really crucial performance optimization. This is a pro tip for when you're chaining a bunch of operations together on really, really big collections. We're talking about views. Okay, so by default, every operation you do on a collection is strict. Let's say you have a list with 1,000,000 items, and you do a map and then a filter. What happens is Scala builds a brand new intermediate list of 1,000,000 items after the map, and then it builds another new list after the filter. That can be a huge waste of memory and time. But if you just stick .view on the front, everything changes. It becomes lazy. No intermediate collections are created. Instead, the very first element goes all the way through the map and the filter. Then the second element goes all the way through. It's like an assembly line instead of building entire warehouses of parts at each step. For big data, this is a lifesaver. So what's the big takeaway here? Being an expert with Scala collections isn't about memorizing every single method. It's about developing an intuition. It's about pausing for a second before you type list and asking yourself the right questions. How am I going to access this data? Is it mostly at the head or randomly? Do I care about order? Am I chaining a bunch of transformations on a huge data set? When you start thinking about these trade-offs consciously, that's when you go from just using the library to truly mastering it. That's the expert mindset.